Okay, ladies and gentlemen, this video is going to primarily focus on the examples of how to prove that two lines are parallel, how to use information given to us to decide what lines are capable of stating are parallel. Now, I did forget one theorem on the previous video, so we're going to cover that slide of the notes first. That is one additional theorem in the form of the converse of the perpendicular transversal theorem. The perpendicular transversal theorem said that in a plane, if a line was perpendicular to one of two parallel lines, then it had to be perpendicular to both. So the converse is going to read similarly. If two lines in a plane are perpendicular to the same line, then those two lines are parallel. So this is going to be a special case situation. We won't use this very often, but if, as the picture is marked, L is perpendicular to Q, and M is perpendicular to Q. If both lines are perpendicular to Q, that is enough for us to state that L must be parallel to M. So basically we have a bunch of tools that we can use to prove that lines are parallel. We have the converse of each of our theorems from 3-2. The corresponding angle postulate, which says corresponding angles are congruent. So if corresponding angles are congruent, that's enough to state they're parallel. We have the alternate and interior angle theorem, which says alternate interior angles are congruent. We have the alternate exterior angle theorem, which says the same thing, except for alternate exterior angles, etc. And each of these can be used. So here we go. Here is a picture. We have three lines being transversed by a line P. We have 6 numbered angles in this picture, but really we don't care about all of them. We only care about the ones that we're given information on. We are told angle 1 is congruent to angle 6. So go into your picture and mark angles 1 and 6. Now notice that we are not using line M. So the first thing we should do in our heads is we should completely ignore line M. I am blanking it out of the picture entirely. You won't be able to do that because you don't have the technology that I've got. Okay? Now, if we look at what's left, we should be able to identify what type of angle pair we have here. Okay, so in our mind, what we do is we think, what kind of angles are those? Well, those are alternate exterior angles. So the converse of the alternate exterior angle theorem says that if we have a pair of alternate exterior angles that are congruent, which we were given, okay, which means it is true, no matter what, we were given that angle 1 is congruent to angle 6, and we recognize that those are alternate exterior angles, then what we can say is that means that L must be perpendicular to N. And the reasoning is the converse of the alternate exterior angle theorem. So you notice I'm using some abbreviations here. You are allowed to abbreviate some words but not others. That is how we'd answer that question. Let's do another one. Okay, so now same picture. You'll notice line M is back because we might be using it now. Now we are given that angle 2 is congruent to angle 3. So again, we're going to go in and we're going to mark angles 2 and 3, which means that we are not using, and I'm going to just, well, basically take your hand and cover up line N because we're not using it. Okay? Then we look at what we've got. Well, angles 2 and 3 we should recognize as being alternate interior angles. Yes? So if alternate interior angles are congruent, that means that the lines they lie on, L and M, must be parallel by the converse of the alternate interior, because these are alternate interior angles, alternate interior angle theorem. So essentially we have, depending on the vocab, we have a converse for every vocab word we've developed. So if the two angles they tell us about have any relationship that can be described with one of our vocab words, we have a converse postulate or theorem that can state that the lines are parallel based on that information. Let's do another one. Okay, this picture got more advanced, but the process did not. We're still given one set of angles, so we are given that angle 1 is congruent to angle 9. So we go into the picture and we mark angle 1 and angle 9, which means we are not using the entire left side of this equation, or of this picture. So in our heads, we should go in and we should cover with our hand the entire right side of the picture because we're not using it and we don't need it to distract us. So we look at angles 1 and 9 and we decide what kind of angles they are. In this case, they are corresponding. So since they are corresponding, that means that if they are congruent, the lines that they lie on, which are lines N and Q, must be parallel by the converse of the corresponding angle postulate. Now, there is an abbreviation for corresponding angle postulate that I will be using in proofs. We're going to use the abbreviation CAP for that. But you would still have to write converse of in this situation. Let's do another one. Okay, this time it's a little bit different. We are not given that two angles are congruent. We are given that angle 1 and angle 6 are supplementary angles. So we go in and we mark angle 1 and angle 6. Notice how we are not using the bottom half of the graph. So we're just going to cover it up with our hand. Okay, and then we look at what we've got. Well, those two angles are both exterior angles. They are on the same side of the transversal. That makes them consecutive exterior angles, which means that line L is parallel to line M by the converse of the consecutive exterior angle theorem, which says if a pair of consecutive exterior angles, like 1 and 6, are supplementary, then the lines that they lie on must be parallel. I think there's one more of these. Yep. Angle 8 and angle 13. So once again, we are given a pair of angles are supplementary. The measure of angle 8 plus the measure of angle 13 is 180 degrees. So what we do is we go in and we mark angle 8 and angle 13, which means we are not using the left side of the graph. So we completely ignore line L entirely. Everything on it is inconsequential. 8 and 13, those two angles are consecutive interior angles, which means if they are supplementary, the lines that they lie on, N and Q, are parallel by the converse of the consecutive interior angle theorem. Okay? So that's how we handle these problems. We are able to look and see, okay, well, if those things have that property tells me that these lines are parallel. Okay? All right. So the other problem type we could see could actually embed some algebra skill. So we're going to go through a couple of those. They're similar to what we just did, though. So here it says, find the measure of angle MRQ so that line A is parallel to line B. Show your work. So in that picture, don't get lost in the notation of the three-letter naming of the angles. You know how to handle this problem. Okay, we've got two angles in that picture that have markings. So the thing we should do is we should ask ourselves, what kind of angles are the angles marked 5x plus 7 and 7x minus 21? Well, they are alternate interior angles. So if they were equal, that would be enough to state that A is parallel to B. Okay? So if angle MRQ is congruent to angle, and we need a name for that one, let's call it NPR, that would be enough to state that A is parallel to B, because we would have the converse of the alternate interior angle theorem. So that what that means is we have to make it so that those two angles are congruent. If those two angles are congruent, their measures would be equal. So we go in and we plug in 5x plus 7 for MRQ and 7x minus 21 for NPR, and we solve for x. We need x in order to state what value we have for the measure of angle MRQ. So to solve that, we would move the x to one side by subtracting 5x from each side. While we're at it, we're going to add 21 to each side so that we isolate our variable. That gives us 28 equals 2x. Then we will divide each side by 2, which would give us 14 equals x. Now, in some problems, we would be done here, but this does not say find x. This problem says find the measure of angle MRQ. So what we need to do next is plug that 14 in to the 5x plus 7, because that is the marking of the measure of angle MRQ. Yes? C is down here, Q is down there. MRQ is marked as 5x plus 7. So that would be 5 times 14 plus 7, or 77 degrees. So the angle that would cause these two lines to be parallel would be if MRQ was 77 degrees. One more. I actually threw this one in here so that we would have an example of our perpendicular transversal converse. Okay, it says find the value of y so that m is parallel to n. Show all your work. Well, in the picture, L is perpendicular to m. So the way that we would guarantee that m would be parallel to L is we already have that L is perpendicular to m. If we also had that L was perpendicular to n, that's what we're going to have to show. That would be enough to state that m is parallel to n by the converse of the perpendicular transversal theorem. Okay, so what we need to do is we need to show this. Well, if L is perpendicular to n, that would imply that this angle would have to equal 90 degrees. So what we do is we say, okay, well, let's make y equal 90 degrees by setting for y plus 10 equal to 90, and then we solve for y. So we subtract 10 from each side, gives us 4y equals 80, and then we divide by 4, which gives us that y is 20. And if y is 20, then this is a right angle, and m and n must be parallel. So that's how we do those type of problems. We identify what angle pair we're dealing with. We figure out what property those angles should have. Should they be equal? Should they add to 180? Should one of them equal 90? Just whichever rule we feel like we can use, and we set up and solve an equation. Okay, that's it for the non-proof examples in this section. There will eventually be more videos in this section, but for now it's just 2. Good luck, and thank you for your attention.